I'd like to thank the organizers. It's been a wonderful week. I think everyone has been really enjoying all the talks, and everyone is also a bit tired, so there will be some movies to relax a bit. So today's talk is going to be about the decrease of genetic correlation with distance and long-range dispersal. What do I mean by genetic correlations? Sample two individuals in a population at two different locations and compare their genomes. And something that we're interested in is how close their genomes are. What's the proportion of genetic similarity between these individuals? And more important, what is the expected proportion as a function of the distance between these individuals? And how this genetic similarity depends on the distance also depends on some parameters like the mutation rates, the population size, and the migration history of the population and the individuals within the population. And why do we expect the genetic similarity to decrease with distance? It's very intuitive. Individuals who live far apart have more ancient common ancestors. Like their most recent common ancestor is probably older than people who live close to one another. And so if their common ancestors are older, then their genomes have had more times to accumulate mutations since these common ancestors. And so the genomes will be a bit more different than people who have more recent common ancestors. And the aim of all these studies is to try to use this decrease of genetic similarity with distance to learn things about the history of populations and migrations by looking at the genetic composition of populations. Okay, so I won't show you any data, but this is the motivation for me to look at these questions. And these questions have been studied for a very long time, almost since the beginning of population genetics. And Wright coined the term isolation by distance to say that populations who are separated by several steps of migrations will be more different than populations who are separated by fewer steps. And this led to a lot of studies by Malécot, Kimmerer, and West. I cannot cite everyone. And there is a sort of universal shape of decrease of these genetic correlations that you expect in mathematical models, for example, in stepping stone models, but also models in continuous space like the one I'm going to talk about. And the shape of the decrease of these correlations depend on the dimension of the space that your population lives in, and it's predicted by an analytical formula that is quite well understood. And all these studies are based on the assumptions that people don't move very far during their lifetime. There's a kind of short-range dispersal assumption. And by short range, I mean a finite variance movement. And what I'm going to be interested in, and the things I want to talk about, is how these patterns of genetic similarity are affected by long-range dispersal events, so rare events where individuals are able to disperse offspring very far from their location, and how frequent do these events have to be to affect the patterns of genetic similarity in the population. And the model I'm going to present and talk about is the spatial Lambda-Fleming-Viot process, which you've heard about yesterday in Apolline's talk. So let me present it again. It was introduced by Nick Barton, Alison Etheridge, and Amandine Véber to model populations who occupy a continuous space as RD. And I'm going to assume that the genetic types all belong to the interval 0, 1, so there can be infinitely many types. I don't care. In fact, I want to have infinitely many types. And the state of the population is going to be represented by this function rho of t, which in each location gives me the distribution of the genetic types at this location. So it tells me if I sample someone in this location, what is the distribution of this type. Okay, it's not defined exactly everywhere, but let's imagine it is. And this function evolves through a series of reproduction events, which are drawn with this distribution pi, and each reproduction event has the time at which it happens, the location x where it happens, an impact parameter u, and a radius r, and at each reproduction event, I first sample a type uniformly in the ball, and this type is K0, and then I kill a fraction U of the individuals in the ball, and I replace them with types K0. So there's a kind of replacement procedure, and I'm going to show you if, yeah. So I started here with 2 types and a frequency close to 1/2 everywhere. And you see after the first reproduction events, in some cases a type 1 reproduce, in some cases a type 0 reproduce, and so the frequency fluctuates a bit around 1/2. And if you let the process evolve, you will see these patterns developing here. And yes. And you can do this with as many alleles as you want, and in fact with a continuum of alleles, and the process is still well defined. And since I'm going to be interested in this shared ancestry weighted by the number of mutations that you might have accumulated since your last common ancestors, I'm going to add mutations in the model. And I'm going to do this in a very simple way by just assuming that at rate mu, each individual forgets its type and samples a new type uniformly in 0, 1. And so it means that the distribution of genetic types is attracted to the uniform measure with this force mu here between reproduction events. Okay, so I have a balance between this mutation force and the reproduction events, which really encode a genetic drift in this spatial model. So it's a very simple model. I'm making lots of assumptions that you might be worried about. I'm not going to be worried about them for now. Most of these assumptions are here to make the model tractable, including the fact that the population density is constant and it's uniform and doesn't move because I always replace with as many individuals as I've killed. So the population size doesn't move. And there's obviously, from the description that I gave of the process, there's a genealogical interpretation and a genealogical structure encoded in the process. And it can be seen in this way. If you sample individuals at k locations, x1, x2, xk, you can start a process of a sort of system of random walks at these locations. So this xi1, xin is the system of random walks, and you start them each one at the locations that you sampled. And then at each reproduction events, when a lineage is in the region affected by the reproduction events with probability u, it jumps. And all the lineages that jump in the same reproduction events coalesce, and they move to a new location sampled uniformly in the ball. Okay, so it comes from the fact that just after reproduction events, you have a fraction u of the individuals that you've just created, and they're all offspring of the same individual who reproduced, and a fraction 1 minus u of individuals who are already there and just survived the reproduction events. So that's what's described here. And the mutations are just equivalent to killing my lineages at rate mu, because as soon as I have a mutation in the lineages, I don't need to know what happened before to know the types of my individuals. So a complicated description, but this is what it looks like. Okay, you sample individuals here at the present. So the present is the bottom and the past is at the top. And if you sample all these individuals, each time there's a reproduction events, they can jump. And when 2 of them are close enough that the reproduction events affects both of them, they have a probability of coalescing. And you see that if these lineages start close to one another, they can coalesce before the first mutation. And some lineages have a mutation before coalescing with any lineages. Some lineages can cross one another before coalescing or before having a mutation. But okay, there's a genealogical interpretation of the model, and the mathematical translation of this interpretation is the following. If you sample a type at a location that itself is sampled at random according to a density function phi, and you want to evaluate the expectation of psi of kappa, where kappa is the type that you sampled, you have 2 ways of computing this expectation. One is with the forwards in time process rho, where you just sample a location x and then evaluate psi against the distribution of types at location x at time t. That's the forwards way of calculating things. But there's a backward way of calculating things. You first sample the location x, and then you start a lineage at x. You run it for time t in the past, and you look at the proportion of types, or the distribution of types at the location of this lineage, and you take the initial proportion of types. So, and the fact that these two quantities are equal tells you that these lineages correspond to a notion of ancestry in the population, and it works with as many lineages as you want. So this is the formula for 2 lineages, and if you've seen the formula for 2 lineages, you can guess the formula for k lineages. So if you sample 2 types, you have the forwards way of calculating expectations like this, where you evaluate with the proportion of time of genetic types at time t at the 2 locations. And you can also start a system of these coalescing lineages at the 2 locations and look with the initial distribution of types, and given how many lineages I have at this time and where they are, you can compute the expectation. And you see here there's a product over nt, and if you start with 2 lineages, nt is either 1 or 2, depending on whether the lineages have coalesced or not. And this is actually what we're interested in calculating. We want to know the probability that the 2 lineages have coalesced by some time or not. And the way of computing things is, is to compute the probability that the 2 types that you sample are the same. Because if you start with initially a continuum of types with no Dirac mass, it means that if you sample at time 0, your individuals have a probability 0 of having the same type. And so, the probability that the 2 types are equal because their 2 ancestors who are different have the same type is 0. And this is this expectation here. This one is 0. And the only way that the 2 guys can have the same type is if they have a common ancestor that is more recent than the last mutation in their lineage. And this is the probability here that I've written here. And using the duality formula that I've written, you can compute this by computing an integral of this indicator function against the distribution of types at the 2 locations. And usually we do things with the dual process because it's easier, and then deduce things on the forwards in time process, and I'm going to do the reverse. I'm going to compute the bottom expectation to learn some things about the probability above. And in order to compute things a bit explicitly, I'm going to zoom out of the process. So rescale space and time in such a way that I have a convergence to a nice object. And to do that, I'm going to assume that for now, I have a fixed radius of reproduction events. All the events have the same radius, and a fixed impact, un, which goes to 0 as n goes to infinity. I'm going to assume that the mutation rate is low enough that I can rescale time and see not too many mutations. And this is how I rescale time and space. So I look on spatial scales of order 1 over delta n, and I speed up time by n over delta n squared. And if your assumptions here are satisfied, then the stochastic process rho n converges to a deterministic limit rho t, which solves a simple equation where you have diffusion and this mutation force that is pulling you towards the uniform measure. And okay, the constants are explicit, but never mind. So lambda here is the uniform measure on 0, 1 at each location. And you can see that if you wait long enough, this deterministic process is going to converge to the uniform measure everywhere, because the types are spreading and the mutations are putting in new types all the time, and they're pushing you towards the uniform measure. But the limit is deterministic, which means that, and absolutely continuous. So this expectation here, if you replace with the deterministic limit, you're going to get 0. Okay, for t sufficiently large. Because if you sample according to the uniform measure, you're going to have probability 0 of sampling the same types twice. And what this means here is that the shared ancestry in this regime is actually quite rare, or recent shared ancestry is quite rare. And the way to capture the amount of shared ancestry that you have in your process is to look at the fluctuations of the stochastic process around its deterministic limit. And this is what I do here. So you take the difference between your rescaled stochastic process and its deterministic limit, where you've started things from the uniform measure, and you multiply this by a large constant. And you choose the constant well, so that Zn converges to a nice limit Zt, which is a Gaussian process in a functional space, which solves this stochastic partial differential equation, where you still see an effect of the diffusion, which is an effect of the spatial motion coming from the reproduction events. You still see an effect of the mutations, because recall that Z is proportional to the difference between rho and the uniform measure. And you have this noise here, which is putting in some randomness at each time. And this noise here is essentially space-time white noise and even space-time and type white noise, with the constraint that when you integrate Z over the type space, you have to get 0, because you're taking the difference between two probability measures. And this Z here is actually quite nice, and you can compute a lot of things about it, and you can compute the correlations between different locations in this Z. And plugging this in this expectation that I had before, I can compute an estimate of my probability of identity by descent if I sample the two types according to a given function phi. This probability will be this small constant here, which comes from the factor in front of Zn, some constant, and an integral over the sampling locations of a function which depends on the distance between the two locations. And this function is, not very surprisingly, the same function that was predicted by all the papers that I cited at the beginning of the talk. So it has this nice expression, and you can write it in terms of a modified Bessel function. It's exactly the approximation that you can find in papers like the one of Barton, De Police, and Etheridge. And it works in any dimension. And so this is in dimension 1. It's actually an exponential function. And if you increase sigma here, which you can notice from here is essentially proportional to the radius of reproduction events. If you increase sigma, then the decrease gets slower. Okay, this is in dimension 2. It still looks exponential far away, and there's a small peak near 0. And in dimension 3, it has an even steeper decrease. And let me show you. So I cannot really show you ZT, but I can show you what the stochastic process looks like when it's close to its deterministic limit and it has the small fluctuations in it. So you see that it's trying to remain close to the uniform measure everywhere, and you have these fluctuations here which can diffuse in space, and the formula that I've shown tells you exactly how fast the correlations decrease in this process. And it predicts exactly like what we had for the approximation of the identity by descent probability. Okay, and now comes the really new results that I want to present, and this is a joint work with Bastian Wiederhold, who's a PhD student at the University of Oxford, and it's actually mostly his work that I'm going to present for now. And the spatial Lambda-Fleming-Viot process that I presented is really nice because there's a natural way of including long-range dispersal is just to choose a fat tail distribution for the radius of the reproduction events. And you can do the same things that I showed with this fat tail distribution, but actually what we realized is that this does not capture all the ways in which individuals can disperse at a long distance. And we came up with this modification of the spatial Lambda-Fleming-Viot process, where at each reproduction events, you choose not one but two radii, and the two radii have different roles, R1 and R2. R1 is the radii of the ball in which you look for a parent who is going to reproduce. So it's the ball in which you sample the type. And R2 is the ball in which you replace a fraction U of the population. And depending on whether R1 is larger or bigger than R2, you get different pictures for the reproduction events. So to the left, the parent search radius is very big, and the replacement radius is very small. And from the point of view of the parent, it means that it's able to send offspring, a little bit of offspring, quite far away from where it's currently located. Whereas on the left, you look for a parent in a small region and you replace in a big region. So this one looks like there is a forest fire and you wipe out a fraction U of the population in a big region, and then someone from the middle recolonizes everything. Whereas here you have more something that people call grouped dispersal, where you just send a group of offspring very far away from your location. And these two scenarios, I didn't tell you how you choose R1 and R2, I'm going to in a minute, but playing with the parameters, you can have a continuum of scenarios between the two. And we will see that they have very different signature in terms of genetic correlations, or they can have different signature in terms of genetic signature. So what does this look like? So say I start with type 1 individuals here and type 0 there. And here I'm in the first case, so the sunny side egg case, where individuals can send their offspring quite far. And you see that the guys in the middle are able to send offspring away from the current occupied region. And in the other case, it looks a bit different. You have this occasional big replacement events happen, and which can wipe out a fraction of the population in a big region at once. And okay, so this is very general, but we're going to specialize a little bit. And the way we choose the reproduction event is dictated by a measure nu, which now is on has 3 coordinates. And we realized that the right condition for the process to be well defined is to have this integral finite. So you need u times the replacement area to be integrable against the measure nu. And it's fairly intuitive from the point of view of the dual process, because that's exactly the condition for the rate at which lineages jump to be finite. And we're going to choose a specific measure nu like this, and this is how it works. You first choose the replacement radius r according to this power law distribution. And then the parent search radius is going to be the replacement radius to the power b here. And the impact parameter is going to be some u0 divided by n and divided by the replacement radius to some power c. And so if b is smaller than 1, you're in the right-hand side case. If b is larger than 1, you're in the left-hand side case. And the parameter c, it tells you how thin your offspring is going to be spread during large reproduction events. So if c is 0, you always replace the same fraction everywhere. So if you have a large reproduction event, you produce a lot of offspring. Whereas if c equals d, say, then you always produce the same number of offspring, and they're just spread thinner and thinner if you have a larger reproduction event. And you can choose c pretty much everywhere in between. And this measure is, like the parameters are chosen so that as soon as a is strictly positive, the above condition is satisfied. And here's what happens in this case. We set alpha to be the minimum of these 3 things here. And we're going to rescale the mutation rate with this delta n to the alpha and time with this delta n to the alpha again. So before we had alpha equal 2, and now we can have alpha anywhere between 0 and 2. And again, with this rescaling, the stochastic process converges to a deterministic limit, which has a similar behavior, but where now the classical Laplacian can be a fractional Laplacian when alpha is less than 2. And so you already have a signature of these long-range dispersal events in a deterministic limit where you can have very non-local diffusion in the process. And where does this alpha come from? Well, A, if you recall, is here, and it essentially dictates the size of the tail of the replacement radius. So if A is very small, it means that you can have very large replacement areas. And B here dictates the parent search radius. And so if B is very big, you can have very big areas to search for the parents. And these two things can make your lineages jump really far away. So if B is large or if A is small, your lineages are going to jump very far away. And this is why you get these parameters popping up in the exponent of the fractional Laplacian. But again, it's a deterministic limit, so we don't see the coalescence in this limit, and we can look at the fluctuations of this process. And it's similar as before. We look at the difference between the stochastic process and the uniform measure, and we multiply it by a large constant. The large constants can have different forms depending on A, C, and D. And we've chosen the constant well, so that Zn converges to a Gaussian process Zt, which solves the same kind of SPDE as before. But now the Laplacian can be a fractional Laplacian. And W here has a covariance, which is given by this expression that I'm just writing here again. And this pi phi here is just, as before, phi minus its integral over 0, 1. And it comes from the constraint that when you integrate Zn over the type space, you have to get 0. And K here dictates your spatial correlations in the noise that you get in the limit. And it can be, you can have two kinds of spatial correlations. Either you get white noise, which is the bottom here, or you get correlated noise in the fluctuations process with this power decay of correlations with the distance. And this is when A and C are fairly small. Okay, and with this, you can compute, again, the correlation function of Zt and estimate the probability of identity by descent as before. And it works. I'm hiding all the computations, but once you know what the limit is, it's very easy to compute the correlations. And it's, again, of the same form. You have this small constant here, which comes from the rescaling of the fluctuations, times an integral over the distance between the sampled individuals. And this function here, f, is given in terms of two things. You have the correlation kernel k here, and the transition kernel of the fractional Brownian motion, which comes from when you solve this linear equation here. And okay, so it's a more complicated function, and it's not going to get more explicit than that. It gets a bit explicit if you're willing to take Fourier transforms, but you have to be careful about integrability. So here's what it looks like in logarithmic scale. So in blue, you have short-range dispersal. So when alpha is equal to 2, and you have white noise in the limit, this is the correlations that you get. They decrease exponentially far from when the sampling location is large. And the long-range dispersal, the decrease of these genetic correlations is much slower, the distance. And so in principle, you could try to use this to compare this to real data sets and try to detect long-range dispersal and estimate parameters of the genetic of these correlation functions and how they decrease. So that's good news. A slightly maybe disappointing news is that we started with a process with 3 parameters, and the limiting fluctuations only have 2 parameters. So you're never going to be able to estimate the 3 parameters with these formulas. But okay, it's something you have to live with. And with this, I stop.
Thank you very much, Raphaël. Are there some questions?
So thank you very much, Raphaël. My question is about the relation with the talk of Apolline yesterday, where there were ghost particles. Is it possible to have ghost particles and to study invasion? I don't know if it's the best way to do it, but
yes. Okay, a big difference between this talk and Apolline's talk is that in Apolline's talk, she took U equals 1 all the time. So you always replace all the individuals in the ball. So the limiting behaviors are quite different. It is possible, however, to add in selection in this model and look at how these types react to selection, but it gets complicated quickly. But in principle, yes.
Okay, thanks.
Hello. I was wondering if there are some sets of data on which you can test your assumptions on the values of A, B, C, or whether fractional diffusion is more appropriate than standard diffusion.
So I'm probably not the best person to whom you should ask this question. Okay, the correlation function comes from the fact also that you are in RD and there are no boundaries and space is very big. I don't know of any data sets that have done that, but I know that in some data sets the
maybe let me just reformulate my question. You have hints on observations, maybe not even data, but observations, saying that okay, it may be better to look at fractional things.
Okay, and since we're a bit late, maybe the last question.
Sorry, I just want. Okay. So the mutation events are like a house of cards. You forget what your parents were and you just draw a new type. Can you like maybe have a relation between the new type and the parent type in your process?
Yes. So you can define the process with pretty much any mutation process.
Okay.
And you still get a central limit theorem where the mu z is replaced by the generator of your mutation process. But then it's a matter of computing the correlation functions. This becomes a bit more tricky.
Okay, let's thank